shoot. Okay. Oh,
You have a pointer?
yes, we have you all set up here. Yeah.
Well, they send us an email saying.
Yeah, I saw you
Yeah.
on that.
Yeah, it's fine.
We just met in Seattle in.
Do you have any collaborations?
Yeah. Sessions, yes. Also.
Yes.
Yeah, let me know when I can start.
We will.
Not the Euro for the virus. The seminar. The seminar is scheduled on Thursday. I always remember teaching Monday, Wednesday, Friday. So just some people may not come today.
That's okay. So,
So how long have you been Okinawa?
2 years.
2 years. Okay.
Well, almost 2.5.
Before that, in
FIT.
you spend a lot of
FIT, almost 20 years.
Yes. Must be, it's a Florida more than Japan.
Yeah, but I'm home in Florida. I mean, our daughter, we just came, and our daughter is a sophomore here.
Oh, yeah.
Yeah, she's sophomore, and our son is just got admission. He's a senior in the high school. So I see if we work for the next week. Wow. It's almost all the time. It's, mathematics. It's just what's that. Maybe we could put
So you have. Very close.
It's a family.
Yeah.
Well, we'll wait 1 more minute. Yeah, we'll see.
Yeah, no problem.
And then this is also on Zoom, so yeah, there will be people
Also by Zoom. Okay.
joining online, and I'll post this on our YouTube channel as well. Well, with permission. Sorry, I should have asked beforehand. Are you okay with us sharing this talk?
Yeah.
Okay.
Fine. So you want me to stand? I mean, the screen will be visible, right? So,
Yes. Just yeah, wherever you like. So I think that'll be great.
how much is biomass? I think that's quite a big group.
Yes, we have 6 full-time faculty. Graduate students. It's kind of a shrink. Graduate student. That is my reason.
I mean, this is overall problems to get strong good pitch to the problem.
Also have a couple.
Not many. Late is doing, and
Yeah.
one I know the two. Listen,
You so he said that the doesn't come Tuesday. So he also from Tuesday.
Yeah, a lot of people are busy today, unfortunately. Very sorry about that.
no,
But yeah, so we might as well get started. So I'm very happy to welcome Professor Ugur Abdulla. He's from the Okinawa Institute of Science and Technology in Japan, received his PhD in mathematics from the Soviet Union Academy of Sciences. And prior to, so I mean, you have quite a CV, but just for brevity, I'll pass a few things. Just jump to the prior to joining OISD, he was a professor of mathematics at the Florida Institute of Technology. So you've been around Florida quite a bit from 2004 to 2022. And he's an expert on partial differential equations, potential theory, calculus of variations, and optimal control, and mathematical biosciences. And he's known for solving an outstanding open problem posed by Kolmogorov in 1928, and proved the Wiener type criterion at infinity for the second order elliptic and parabolic PDEs. So without further ado, please take it away.
thank you very much for recording.
Yes, forward.
It's recording. Thank you very much for a very kind introduction. Yes, today talk is not about this Kolmogorov problem on PDEs, but specifically topic is the cancer detection by impedance tomography and optimal controls here of elliptic PDEs.
And sorry, let me just double check that everything is working here. So yeah, it is recording, audio is working. Okay, excellent. So I'll just hide that. All right, thank you.
Okay. So here's a problem. Electrical impedance tomography is one of the most popular methods for identification of tumor, an overall cancerous tumor, or has many applications. The problem, actually, I got interested in this problem when colleagues from Dartmouth Medical School visited me. They needed some PDE expertise, was almost 10 years back. And in Dartmouth Medical School, this is a very common procedure, how they specifically try to detect cancer, but specifically breast cancer. And you know, breast cancer is one of the most worst diseases where extremely important thing is to detect it early. And this method is quite effective. And so here's the idea. I think this approach is also taken specifically what we use in Dartmouth Medical School, but typical application. You see, this is a cup. There are four slices, and in each slice you have 16 electrodes. In total, you have 64 electrodes. Part of the body, and then you put inside of this cup, and then is this those electrodes you can give a voltage and measure current, or opposite, give a current and measure voltage. And based on this measurement, you try to identify the location of tumor inside the body. Now, this method is based on the fact that electrical conductivity of cancerous tumor is almost twice higher than conductivity of the healthy tissue. So if you can identify conductivity map, then location of this high density places will be exactly because when conductivity of cancerous tumors is known by experiments. So you will find out is location of this cancerous tumor. But this is a very extremely difficult inverse problem you have to solve. And then based on this measurements, either voltage to current or current to voltage measurement, which is finite dimensional measurement, you try to identify infinite dimensional map, conductivity map. So today I'm going to talk about this problem as a new method is developed. I developed a new method and my group. And so today we're going to talk about this method. So here's also a schematic of this situation where you have an electrode and it says 16 electrodes. An important characterization here is mathematical model for this problem is so-called complete electrode model. So that's what we want. First, I would like to describe the model. Well,
I'm sorry to interrupt you, but is there any simple way to describe why Q was higher?
This is just about just fact, because I mean, problems are high density. This is just a biologist. Yeah, this is just a fact, which is their experimental results. I mean, the papers you can see. Most likely due to high density, because the high density and then conductivity becomes the system more closer to solid than than healthy tissue. So that's why. So with a real problem, of course, in 3-dimension or in 2-dimension, because you can consider cross section and try to look at the cross section of this cup. But I mean, mathematical problem can be described in any space dimension. It's a problem is the following. So Q assumes that Q is some part of the body which you trying to identify cancerous tumor. So you're looking to electrical conductivity tensor, which is in general. So this is the matrix, and AIJX is the conductivity, and assuming that it's in general anisotropic media. And we go to identify that. So EL is the M, the little m, the number of electrodes. So in this particular specific application you're looking, M will be in 2-dimensional case will be 16, in 3-dimensional case will be 64. Right? This is the application. But M electrodes. And then Z, the vector Z, also M-dimensional, exactly electrode size. It's called the impedance of this electrode. Impedance, important factor, also characterizes this because environment where this electron is in the body. And I, and again, m-dimensional vector I is a current pattern. So we usually this current, that means you current, electrical current, which you give to these electrodes. This forms vector I, and it's called the current pattern if the sum is equal to 0. So this is conservation of charges. Then you have also m-dimensional vector. It's called the induced constant voltage of electrodes. So again, m-dimensional vector, the voltage on the electrodes, and also it satisfies this condition, which means grounding condition. So you have a grounding. So here you're looking to function so-called electrostatic potential in the whole body, and boundary voltage U unknowns. So first I'm describing now the model which is a forward problem. Assume that we know the conductivity vector, Aij. Then the problem is the following: to find this electrostatic potential, which is a function U, and also boundary voltage, also part of the unknown on electrodes. They satisfy the following conditions. So potential satisfy potential equation, which is a second order elliptic equation, and conductivity is exactly the coefficients. Like, for example, if the conductivity will be constant matrix, assuming that this will be Laplace equation. And that's also the problem. If you're looking to healthy tissue, then potential equation will be just a Laplace equation. Okay? But when you have a situation when exactly like we're interested in, when Aij in general will be L infinity function or matrix function, because you're going to have the piecewise constant in particular. That means in tumor, let's say specific units, this is the real numbers, 0.4 for tumor and 0.2 the conductivity for healthy tissue. So then they're going to have some Aij, the coefficient of the elliptic PDE, when there's a cancerous tumor, will be discontinuous function in general. So you can't solve this, look to the classical solutions here. So this is an electrical potential equation. Then the boundary conditions. Now there are two types of the boundary conditions here. The one is on the electrodes and outside of the electrodes. So outside of the electrodes, you have conormal derivative is equal to 0, which means that it's basically a flux is 0. So you kind of like an insulation. There is no flow. There is no electrodes. And on the conductors, you have the Robin type boundary condition, which is exactly the following form. That means a linear combination of the U and conormal derivative. Here you see the constant ZL is exactly impedance of electrodes. It's a physical constant, which is also known. And this linear combination must be equal to exactly the voltage vector UL. So in this problem, UL is also unknown. It's a non-standard PDE problem. You will use a potential, which is a solution of the PDE, but this constant vector UL is also unknown. Well, therefore, you need one more condition, and that the condition is basically the Ohm's law. Famous Ohm's law is the integral form. If you integrate along each electrode this conormal derivative, the flux, you're going to get the current, IL. So IL will be the input. So that is basically the conditions. And here again, conormal derivative, because we have a general elliptic operator, it's basically defined as this is the definition of the conormal derivative. So that is basically now is, of course, you have an ellipticity condition because positive matrix should be positive definite. So this is the elliptic equation. Potential equation is an elliptic equation. And so that's basically, this model is called complete electrode model. So this is a forward problem. If we know this conductivity, it's basically given electrical conductivity tensor or matrix in this situation, electrode contact impedance vector Z, and electrode current pattern I. It is required to find the electrostatic potential U, and also this electrode voltages. So that's a forward AIT problem, so-called the complete electrode model. Well, this model was introduced in the following papers in 1989 and 92. As the first paper, actually, there was also experimental results showed that this is how accurate this model is, an extremely accurate model. And this, in particular, the second paper in this, the same authors, I mean, one change, they also looked to this well-positiveness of this model, and they proved the existence and uniqueness of the solution. Yes.
So thus far, you have looked at.
Yes.
You will introduce that or
Well, I mean, you're looking to potential equations. So here, there is no time dependence. Because when you have an input, then potential is just solves the Laplace elliptic equation. Okay, there's no time dependence here. Well, you can look some, then you have to use a full Maxwell system if you have a time dependence. But here you're looking to the exactly stationary situation.
I'm asking, is there any to be by considering any
Well, again, is that will be different model. Then you
of course it will be different.
then that will be max. You have to write the Maxwell systems and instead of the elliptic equation. But here you're looking to just conductivity. Given conductivity, you're looking to stationary. So you're looking to
Playing with kind of inputs, for example, you can consider things like, way of settling to the equilibrium. So
well that will be a different model. Yes, and I'm not sure this will be. I mean,
extra information that might help to solve the problem.
maybe, but I mean, this time dependence is not going to simplify inverse problem. Will make it even more complex because I mean, it will be equation will be then, as I said, Maxwell system. So you have solved inverse problem for Maxwell system. So, but here you have an elliptic equation. But the problem in nature is the time independent. You're looking at time instance. Okay. All right. So here it's basically now our main problem is yes, please.
I just have a very basic question. Could you help me visualize all of the conditions you have written down in terms of the physical picture?
Yes.
Yeah. So, what, you have the no flux, which I mean, that's the current, and there's various conservation things and et cetera, but what is the way? Something concrete.
Well, I mean, we're going to come to concrete examples here. Remember at the beginning, I showed you this in three-dimensional space, your domain will be exactly this, for example, cylinder. Okay, your domain is a cylinder, X, Y, Z. Okay, and then you see this is inside, but on the boundary, you have an electrode. You see this inside part, this is your boundary, right? The boundary of the cylinder. There's a top, bottom, and on the lateral surface, you have electrodes. So you see, think about this problem now. Electrostatic potential inside of the cylinders in three-dimensional space, X, Y, Z, solves the potential equation. Okay, Aij, your coefficient, which is given in, if you know this is the conductivity of the tissue inside of the body. So therefore, this conductivity, if there's, let's say you have some tumor inside, conductivity will be equal to certain constant in this tumor, but outside tumor will be equal to different constant for healthy tissue. Okay, so then boundary conditions. Whenever you have outside of the electrode, because you give it input voltage or current to voltage through electrodes. So outside of that, you have a flux, there's no flux. Therefore, du dn is zero. Flux is zero, no flux. But on this, that was exactly the main paper as experiment. On the electrodes, where you're giving this, for example, current measuring the voltage, then you have a you have exactly Robin type boundary condition, which is exactly this. Okay. So this is the reason. This no flux condition. On the electrodes, you have this condition. Okay. Well, this is again experimentally revealed this condition. Novelty, I mean, this condition is also kind of well known, right? You see the conormal derivative, but you have u minus ul, right? This is input. So it's basically telling you that flux is proportional to the u minus ul. The ul is a voltage over there. That's clearly condition. The novelty of this paper was introducing here ZL, this vector ZL, which is impedance. Because when you're doing this in the body, you cannot take this coefficient specifically like 1, but ZL, which is defined exactly with the properties of this body. So that's probably boundary condition. And this is just an Ohm's law integral form. This is basically, you see this, if you integrate this flux along this electrodes, you're going to get the current. Okay. Okay, so that's a problem. So this is your forward problem. It's a non-standard PD problem. You're given J is known, CL is known, IL is known. You try to find the U, little u, which solves the PD problem, and also this constant vector UL voltages.
Is it fair to say that so the entire boundary so the places where you have electrodes in the
Yes.
side is so
Yes.
so that's if you consider integral cross section of each of the electrodes, you get a total through that, which I presume is I. Right?
Yes, but this I explained, right? So this is insulation, no flux, and the flow is basically all this Robin boundary conditions. Basically, use a flux is proportional to the difference, potential difference. UL is the voltage, constant voltage on electrode, but this UX is solution process, potential in the okay. So that's basically forward problem. As I said, well, I mean the forward problem is a well-posed problem. That means forward problem has a exist and unique solution, stable solution. So it's just, that means if you know this input data, this forward problem is a well-posed problem.
You have this coefficient.
Yes, that's positive, definitely. This should be a Elliptic equation. As I said, if you have a healthy tissue, right, completely, then that will be Laplace equation. And then this will be just a constant times unit matrix. And that will be just Laplace equation. In fact, the Dartmouth Medical School, the problem was that they were trying to solve this, apply this model just for solving this for Laplace equation. And then I said, well, I mean, that's what when they came, that's what I said, well, I mean, this is when you look to this cancer detection model, this will not be Laplace equation. This will be elliptic PDE with bounded measurable coefficients, discontinuous coefficients. So you have to understand that we have a beautiful theory in PDE for this, like Milgram theory, of which we can solve the elliptic PDE with the general conditions. So that was one of the starting point when they came, so understanding this problem. Okay, so now basically this model, I think the second paper is basically they proved well possible. So it's existence and uniqueness of the solution under elliptic condition. So all is good. But now that's a problem which we're looking inverse problem. That means we don't know AIJ matrix, okay, because that's cancer detection is exactly required to find AIJ. So that's basically inverse problem is formulated. Given electrode contact impedance vector, so Z is known, this is experimental, for body is specifically constant vector Z is known. Electrode current pattern, okay, that will be your input. That will you choose whatever input you want. And then boundary electrode measurements, and you do input current, measure voltage, do that. It is required to find electrostatic potential U, little u, and also conductivity tensor A. So that means now we have to solve the inverse problem to find U and A, PD's coefficient, the coefficient inverse problem. Extremely ill-posed problem. And this type of problem actually called the Calderon type inverse problem due to the celebrated Calderon's paper on an inverse boundary value problem, which is famous. But this problem is actually a more difficult than Calderon problem. In Calderon problem, you try to identify this coefficient Aij based on the Dirichlet to Neumann or Neumann-Dirichlet map. That means based on the boundary measurement in the full boundary. Okay, so this is but here, pay attention that we have not measurement the full boundary. We have actually here electrodes. That means a finite dimensional measurement. We have to do this with finite dimensional measurement. So that's why it is more difficult than Calderon problem. Based with a finite dimensional measurement, you try to identify an infinite dimensional map. So here is a recent work, which is, I mean, relatively recent work with my group, and it's an ongoing project. And the last paper is just a preprint. It's in the press now. I'm going to talk about this result. And in fact, a new method is developed for solving this inverse problem. And I will demonstrate now the results. So problem which I'm going to consider this problem as an optimal control problem, as you saw in the title. So optimal control problem formulation is a form. So we're going to look to this cost functional. We're going to look to minimization of this functional. Okay. And this will be PD constrained optimal control problem. And here's a V. V is a control vector. The control vector has two components, which is exactly unknown in the problem. That means A, your electrical conductivity map. You don't know A, and you don't know the voltage vector. So this is your unknown. Okay. And then based on this unknown V, it's in a certain space. I mean, this is basically A, you're going to put only in L infinity space because we want to include, in particular, discontinuous maps, piecewise constant maps. So that's very important to have L infinity. There's also a problem here is you can't make it smooth if it is smooth, but then you lose in the real problem. You want to include this discontinuous. And U is I mean, but A is also we put some intersections and some Sobolev space H epsilon due to this mathematical results, and then this is the basic control set. Use it just finite dimensional vector. Now here, given this control vector A and U, your constraint will be the PD problem. You're solving the whole PD problem. If you pay attention here, this is now just a mixed boundary value problem for elliptic PDE. So potential equation, elliptic PDE, and the boundary condition Robin and Neumann boundary condition, mixed problem. So this is the, by itself, if you give any control, the problem is solved. So there's a weak solution, which has nice properties like Snugden theory. But if you notice, one condition is missing here, right? This condition Ohm's law went here to the cost function. So this is if you pay attention, this is exactly the same Ohm's law, because we see this from here, this ratio, this UL minus U divided by ZL will be exactly the UDN if you solve this problem. So that will be just Ohm's law. So kind of this optimal control cost functional want to minimize discrepancy in the Ohm's law. So you try to find the control for which this will be minimized. If it is zero, explicit solutions will be zero, for example, so no negative. It's minimized, and then you will solve this condition. Okay, so that's the kind of optimal control frame we're going to look to this problem. Well, I mean, by itself, this is an optimal control problem. It's a nice statement, but it doesn't make any ease because I mean the same problem formulated here. So that's not the main point here. So but we're going to solve an optimal control frame. So here's basically then, in particular, this formulation is a very powerful actually. In particular, you know, this optimal control problem includes also forward problem. By the way, when you look at the forward problem, then we know that we know A, right? We just unknown is just U and U. So particular case, if you remove this A from the control space, that means you know this matrix, then you get the following problem, which is just the optimal control problem, gives you this particular case, gives you the forward problem. And this is actually a problem is a convex optimal control problem. It has a unique solution. So you can actually, with this method also, generate this solutions forward problem, which will be unique minimizer of this convex optimal control, PD control optimal control. So that's just one particular case, but here's the main thing. So what's the main idea? So the main idea, which is held here, I mean, again, idea like from combinatorics, pure mathematics, idea was the following. Now, the main problem here, why this inverse problem is an ill pose, because with a finite dimensional measurement, you try to identify an infinite dimensional map. So question was, how can we increase the size of the measurement, but to keep the size of the unknown the same? One idea, I mean, this idea actually was in the field that says that, oh, maybe we can increase number of electrons, although some restriction over there, but this idea doesn't help. Why? Because, I mean, first of all, there is some, of course, physical, technical situation. You cannot put million electrodes over there, right? There's a certain number. This is exactly the number which is used in the field. But the second also, look, if you do the more electrodes, or you do more input, like if you do the one set, second set, each time you put the input I, you increase the size of the unknown because the voltage which is measured, it's also unknown as a problem. So therefore, this doesn't help. But then I get here the idea is the following. Very simple idea, which guys will see how it makes a change in this problem. Well, I said the following. Let's do this. We take first set I, right? First input current and measure the voltage. Then I take this measured voltage and consider various permutation of that. And specifically here, I describe a circular permutation. You see, first set from 16-dimensional vector. I do the permutation. Permutation, for example, I took the number 1, put in 16th place, 16th, so I just rotation change. So then this new set of voltage I'm using as an input. But this is permutation of the first measured voltage. And then I measure current. This is very easy to also apply in medical situation. Gives the voltage, measures the current. So then the second set of current which I got becomes the input. But if this is an input, pay attention that voltage for second set voltage will be just a permutation of the first measurement. So unknown is the same. So the idea was that if you have, let's say, vector size 16, it's a two-dimensional case even, how many permutations you can make? 16 factorial. Or in 64 factorial, which is a huge number. So you don't need to do all the 64 factorial, but the idea was that we can actually can increase the size how far we want, up to 16 factorial. And the idea that unknown size will be the same. Does this help to solve the problem? And that was basically the key idea here.
Do you want to consider all permutations or all corresponding?
Well, all permutations, if you do 64, it's impossible number. 64 factorial is a number which no computer can handle.
Right.
But there will be certain number of permutations. My question in particular will be, what would be smallest number of permutations which will give me good resolution to find the tumor? Okay, and that's basically what's the problem we want to describe the results now. So but here's the thing. What price I have to pay for that? Now the price which you pay for that, because each time you increase the size of the input current and the loop current, then mathematical context, what I do, I'm adding a new PD constraint. You have to solve the PD problem again, this current. So the price I have to pay for this idea that number of the PD constraint will increase. For example, if you have in original problem, I described one PD problem, right, which you have to solve. But now if you do, for example, certain number of new permutations, each permutation will require adding another PD constraint. Well, I mean, but this is not a big problem because, we can solve also several PD constraint optimal control problem. But this is, of course, increase the complexity of the problems. Here's a problem formulated. Look what I described your problem. I just take here, you remember the number of electrodes in M, and I'm adding just M new permutations. And by using this rotation scheme, first goes to 16, and then I rotate. So number of input data now will increase from n to n squared. That means if 64 will be 64 squared. And we'll see if that actually that was enough to get quite a nice result here. But this is basically now I described optimal control problem. When I did exactly this, M is a number of electrodes. I'm looking to exactly M new permutations. That means input data will increase from M to M squared. Okay, and that's the main problem. My cost functional is this. I'm minimizing this cost functional, but PD constraint here is supposed to change. You see all this vectors sitting here, and so that's basically this is also input data. I will be 64 squared in this case. It's three-dimensional, or 16 squared, 256 in two-dimensional problem. So now here's a basic. Now I would like to describe the results now. First of all, to solve this problem, again, idea was to use infinite dimensional calculus tool, prove the Frechet differentiability in the balance space setting, find the Frechet gradient, and then use the projective gradient method in balance spaces. So that was an idea of using the method. But this is a problem, is two problems, right? Original problem, and this is a chain problem after adding this new permutations. And so this is an adjoint problem, since I'm using this optimal control framework. So that will be adjoint problem. Adjoint problem is similar elliptic problem, okay? And the boundary condition includes also some new term, which comes from cost function. So that's an adjoint problem. And here's the main result on Frechet differentiability. I'll briefly now explain mathematical results and then show the numerical application.
So you get the adjoint problem taking the variation.
Yes. Adjoint problem, because you give a variation, it's optimal control problem. You give a variation increase to optimal control, and then you calculate.
It's also difficult because your cost functional is quite.
Yes. So that's an adjoint problem, fine. And here's the main result, mathematical result. The cost function is differentiable in the sense of pressure in the balance space in this control set. And the gradient has a following formula. You see, pressure gradient has two components. But you see, the derivative with respect to a conductivity vector, you see, includes here a joint problem as well, direct forward U and a joint problem. And the component of with respect to U, and then this is also formula for pressure gradient. So I'm going to that, and then based on that, we prove this convergence of this gradient method in balance space. So that's a projected gradient method, how it looks. And if you have a conductivity matrix, you see at This is the gradient formula, so you move in anti-gradient direction because you minimize to exactly to unit. So that's a gradient, projective gradient method, because you have to also project. So I'm going now very briefly, what is done here. We proved first mathematical result, existence of optimal control. Then Frechet differentiability, projective gradient method in one space setting, and also what is proved here, convergence of the method of finite differences. We can discretize a problem. Optimal control problem is discretized. So this is a very brief one. This is a discrete problem. And then after discretization is basically we have this as the result, convergence of the method of finite differences. Convergence with respect to functional and with respect to control. Again, very brief result. And in particular, actually, this also required some beautiful results in functional analysis. This came out from here, embedded to Hilbert space of solid space of mixed smoothness as a different search. But this is basically was one of the tools which we used here. Now, what I'd like here now is to look to results. Yes.
So when you find differences, what kind of measures are you considering? Kind of measures, spatial measures.
Yes, cylindrical domain. You divide this little rectangular domains and then covering this from inside and outside, and then doing this finite differences method exactly like that in PDEs and applications. Yes, I approach about from inside and outside with small cubes. Okay? Yeah. From inside and outside, and then you build, and then you see. I said you talk here multilinear interpolations. When you solve the discrete problem,
you're not using geometry.
no, this is, I mean, when numerical solution, in particular, finite element method also could be used. But this is a convergence of the method of finite differences. Here, this is also theoretical results in a sense. But when you do this, that's actually a question. When you do this numerical calculation, actual method of finite elements is more effective than method of finite differences in this particular situation. So, but that's basically finite difference element. Now, all right, here I would like very briefly say now this results, computation, simulation, and application. I actually divide way that to explain how will be simulation and also specifically in clinical situation as well. There are three stages here. Now, stage one, I build the problem. We can build problem where we put tumor in certain positions. So we build the problem. So that's what simulation, right? We select boundary current pattern against the conductivity matrix ourselves and just simulate the EIT model example. And by solving this, remember this forward problem, convex optimization problem. Now, in clinical situation, what does it mean? They will just have to implement the current to voltage procedure. That means in clinical situation, you don't have to simulate. There is some certain tumor in the body, maybe, as they try to identify. You just give the current I and measure voltage. So that's what's done in clinical. But in our simulation, of course, we created a problem with certain tumors. I'll show that example. Now, second stage, then I don't use an idea permutation. Just solve the problem, one PD constraint as it is. This data is equal to 16. You do the Frechet gradient method and you solve the problem. The same thing here also you did clinical situation, right? Imagine that what we did in clinical situation, you did input current voltage. We have a software gradient method for this problem. You take this measurement and then solve your problem and find and to see what you get, right? So that's basically what we have here. Now, finally, the third stage, that's where his idea is used, permutation. So here we look to apply, as I will explain, we increase input data from m to m squared. We do the circular rotation principle, increase the data. Exactly, I will explain this part here, right? And then we solve this problem in general, and then try to compare the solution. So this is actually in clinical application will be a situation will be the same. To improve the size of input data from m to m squared, we implement voltage to current procedure. So this clinical application will be this. First, input current, measured voltage. You take this with voltage vector, measured voltage vector. We're looking to this m new permutations. Each permutation, we're doing this at input and measuring current. Could be easily done. It's very cheap, very not expensive, because this is very, less than seconds time, because you just do voltage, current to voltage measurement. So that's it. And then, of course, with this data, again, we solve with our methods of problem. Now, here I would like now to explain the results. Okay? Now, I show numerical results first in 2D and then also 3D. So 2D numerical results in the 2D. So this is basically in 2D, you're solving this in the cross section, this formulation region. So this is red are exactly electrodes here, 16. And size also specifically will they do in the medical situation. Total length or area of this electrode should be 60% of this whole. So that's basically what medical situation we do. Here is specifically, a finite element method, and this is the size which is for at every step we have to solve elliptic problem. This is basically sizes and is here, and here's the problem. So look, this is a problem we simulated. We build this problem. This is a model example. Assume that we have one tumor here, right? And size also everything is size exactly the same, like I showed at the beginning critical. Assume that we have a tumor. This is the red. We try to identify this tumor. Now, this is the stage. So that's stage 1. I simulated this problem. Stage 2, without this idea, we use this gradient method, and that's what we got. Then is nothing, right? And then also post-functional you minimize, but no resolution, nothing is visible. Now here's a stage 3. That means we increase the data from 16 to 256, the two-dimensional case. And then that what is identification, you said resolution is significantly improved and then gives you exactly this. So that's basically how this method works, basically by increasing data. And by the way, one question comes here, is m squared, when doing just m permutation instead of m factorial, we just did m new permutations. If we go to up, increase it, no improvement. Okay? Interestingly, m squared was a kind of like an optimal size. If you do beyond that, complexity increases so much that you add a lot of error. So in a sense, this was an m squared. That's why I demonstrated also here that was the best measurement. Yes, Chris.
So what is Kn?
This is the final cost functional value. Final value of the cost. Remember cost functional K when I do this new method stage 3.
So in stage 2, even if you get this ridiculously small
Absolutely.
cost, but it's still lower.
Absolutely. So you see, you minimize it, but on expense of the unit minimize, it's a ridiculously small value. But you see, sigma is no resolution. That's a very difficult problem. That's an inverse problem. There's non-uniqueness in this problem. And so this is basically, that's exactly the situation. But then when this idea used, then you increase the data, which allowed, cost functional, even though we lose here, right? This is the cost functional, right? I mean, but resolution has become significantly better, right?
And these quantities are what?
Relative, right? Ratio-less. Relative, correct. So now here we have now several analysis, and then I'm going to three-dimensional results. How much time I have?
7.
Okay, good. So then we're looking here at question was this RT we mentioned here, the radius of this tumor. So we would like to see what is the radius, how does radius affect that? So, I mean, just in two situations, this whole thing radius is 0.1 in meters. So it's basically 10 centimeters, which is a kind of realistic situation. So you see the size is 0.03 radius, then it's visible. When you reduce the size, you see resolution becomes worse and worse. And then, I mean, here the size actually smaller than your finite element triangles, and then of course you lose it, you don't see anything. So size is effect. Size of tumor is very important. Smaller tumors are hard to identify. This a lot of calculations done to analyze and reports are always in the paper. And the cost values and everything, how it changes here. Then another important factor, how close your tumor, this is data which I think in medical facilities, they need to know that. So that's important, all analysis done here. How this result depends on how close your tumor to the electrode. Okay, so you see this is the CT is the location, exactly the coordinate of this in this cross section. And so this is, you see, this is the distance to very close to electrodes, resolution is better. But when you move to the towards center tumor, away from the electrode, resolution becomes worse and worse. And eventually when it is right almost at the close, even closer, then you lose the resolution. So location is also important. That's very important.
That's is where the actual tumor is.
Yes, yes. Yeah, that's how that is the very actual tumor. You see here, you feed it almost correctly, but then it becomes worse and worse. Okay. Okay. So, and then this is basically one this again, cost values analysis. And then, of course, numerical result, we have not one simulated example, we have 4 tumors of multiple sizes.
So, but if your data is sort of radiant symmetric, does your method perform? Because it may not be about the distance from the
Yeah.
electrode, but rather how close you are to a symmetric case.
Yeah, I mean, when it's fully right in the center, you have a radial symmetry, but this is the worst.
It's the worst. So, but even if you had, say, multiple, let's say you have 3 spots, 3 tumors.
I'm going to talk about this right now.
Okay,
You'll see now. So you see now 4 tumors. All 4 are different size and locations are different, right? So again, I simulated this problem, stage 1. Stage 2, no new the idea, just one data PD problem, looks nothing, right? Almost nothing, no resolution. Again, post-functional, on the expense of the voltage vector, it goes very fast to 0. You get it in certain space number of iterations, 34 iterations, but you don't have the resolution. Now, then idea is used again, increase from m to m squared. You see 2 big tumors identified clearly, but the 2 small are not. Okay. So, but 2 big immediately identified, but again, size is essential here. Then the question came here, look, what we did here, let's take the smallest tumor and start increasing its size. And eventually you see when its size reaches again, we identify also the small one, but still not the first one, because which is close to the center. So this analysis, again, full analysis here is done. And this is when you do the regularization. But regularization is a cost function. Remember, I had a big U regularization. If you do big U regularization, picture becomes like this. It just cleans out regularization, but it doesn't help much with the resolution because we're not doing the sigma regularization, but U regularization. Sigma regularization is not doing good effect. In fact, the idea of the method which I described, this idea, this is some sort of regularization idea. Increase the data, that's plays role exactly regularization. So this regularization idea is basically coming to that. Now result in 3-dimensional case. Okay, 3-dimensional case. So we have this the cylinder. We use again for calculations of solving PD problem using finite element method. You have now 64 electrodes, and here's the problem. Okay, so let's just simulate the problem. So we look to the situation again. That's the cylinder, and then I simulate this problem. There's 1 tumor here. And here's the base was the result shows that, and we'll see here that in overall, this is the one shows that when you do the process with the idea, again, 64, I'm doing exactly new permutation, 64 rotation scheme, and then doing 64 rotation, 64 new permutations, and then I get data increase from 64 squared, which is 4,000 or something, and more than 4,000. In this case, you see, you identify, if you look to the end of this process, level set of sigma, the true value of the conductivity in the tumor is 0.4. If you look to level set 0.37, you're going to get exactly this red part. So that's how approximately you find the locations of tumor. So, and here again, similar analysis, this is the cross section. In the cross section, this is the true tumor, but in the cross section, after using stage 3 of this idea, we get cross section exactly with this type of resolution, which is quite and gives clearly it tells you that there's a cancer tumor in this case. And similar analysis in 2D, 3D. You see this situation here. This is the cross section. Okay, the 3D, but we're looking to the cross section. And again, stage 2, that means you don't have this idea, just 1 PD constraint. Then nothing is identified here almost in this region. So this result, but then of course identified when this region is, we use idea, that means data increase from 64 to 64 squared. And I mean, this again, how this is the result for 3D, but I'm looking to numerical results on the cross section right on the center of the tumor, which is exactly here, slices, and z equal to 0.1, z-axis is the axis in vertical axis. Here, and then again, how it depends on the size of the tumor. RT is the radius of the tumor. Then again, small size, you lose it, and clearly the last picture is the size is smaller than your triangular mesh, even. So that's why clearly here. Then cost function values here, and then how location from the again, you tumor closer to electrodes, you get a better resolution. Away from the electrodes works. That's basically the situation explained that. Here you move it towards center. The situation, and this is the exactly coordinate of the center of the tumor. Here, And again, here's, I mean, this is again multiple tumors, this 3D, that's also result, one result, and very similar results in this case. Just using this idea, stage 3, if you have a 4 tumors of different size, and then you have this, if you do this method, and then at the end you identify this level set of the point sigma x, where sigma is bigger than 0.35, 0.4 is the true value conductivity, then you get exactly the same. Again, it's not, you can identify the small ones. I mean, one of the things here, because big tumors identification takes all of this optimization source toward them. So small ones are not identified, but similar analysis was done. If you try to increase the size of this small tumor, then you go to identify it, and then closer to center, it's reverse. So that's basically this. And then that's a cross section of the situation. Again, results in 3D. This is the situation. This is exactly cross section of the center of the tumor. You have 4 different tumors, and then stage 2, but stage 3 identifies the big ones clearly. So again, if you take the small one, as I explained, start increasing its size, which is a small one, I increase its size. When size reach certain level, which is this means basically quarter of the radius. Okay, and then if you reach the size, and then basically it's identified. But one of them is the one which is increased, identified, but small one is still not identified. Okay. And so that's basically, I think, this is a picture which also here. Yes.
So what happens if your tumors are not spherical?
I don't think the geometrical shape of the tumor is essential here, but the size.
Have you tried them?
We did, right? I mean, if you can take like cylindrical tumors, you get a similar result. But I mean, again, if one dimension
Is it recognized as one piece or multiple?
it depends on this. If you take it too thin, that will be multiple. It just breaks down. It becomes something like this. So that's clearly the situation. I think that in real situation, what is good here, because we identify tumor as a level set of conductivity. Okay, so level set, you don't expect this nicely placed tumor. So this model example is that. But idea is this, yes, if you do this like cylinder, if the even one dimension is too small, then it's going to break up. Because even you see this effect also here, that instead of spherical, you get something prolonged. Okay?
And it's also, and the level sets are going this. So
Yes, yeah. So that's basically where we are now. This is, and I stopped here. So that's the results. Again, the idea here is, as I said, it's one could think that still in 3D, this analysis ongoing now, that is this m squared the optimal? Could we do more permutations and get a better resolution? So far, we think that m squared is the best. Because when you, until m squared, everything is nice, resolution is improved. But after that, complexity increases so much that error is a lot of error, so it doesn't help. So in fact, there is some optimal size. And as I said, 64 factorial, for example, is a number no computer can handle. It's a huge number. So, but some optimal size, I think this result shows that it's exactly m squared. And the result of this computation, like, I mean, I just give you an example that, for example, to solve this problem is a calculation here. We use a cluster in OS, very nice, very modern cluster computer. So this simulation, I think it took 12, 13 hours. Okay, so it's a very expensive computation when you do this exactly in the situation with m squared, yes.
So I think consider the possibility of accounting for basically, so if you rotate, say, all the electrodes one click, right? So this is a cyclical permutation of some sort, or several clicks. The underlying tissue did not change. The tissue effectively got rotated. Okay, are you accounting for that or not?
No, but I mean, well, look, if you, it's the same idea here, but you have electrodes you can't change electrode position, right? An electrode is sitting here, but we're changing exactly input. You see, from 1 to 16, now 1 will go to 16, 16 goes to 1, and then you just rotate this voltage.
Yes,
that's
correct,
exactly
but underlying, you have to account for the fact that the tissue remained the same. It's just right. Is your method, does it take account of that or not?
I mean, of course, but voltage is different because this is as I said, you see, each time you make an input, right? This is actually look to PD problem, right? Because you have a PD is solved, right? But in this PD is solved, these two PD problems, if they will be the same PD problem, then problem will be again not going to help you, right? So that's why it is a different problem because
No, but what I'm saying is, as you rotated the sort of the inputs, right?
Mhm.
Initially by just, flipping the voltages between electrodes. But if you do this in a way that corresponds to a rigid transformation of the domain, then you know that the underlying conductivity matrix just got rotated, essentially. And you account for that.
we do. I mean, this is excluded because that's also, I mean, because that was counting is basically when you take the voltage input, given voltage permutation, but the tumor doesn't change, it's fixed over there, okay? It's a tumor sits in this position, okay? So you're not going to gain anything. Like, for example, if you do the 64 factorial permutation, there are clearly will be some which will give you the same result. You have to actually count this, okay? So therefore, this is important that we take the rotation principle because I mean input voltage you cannot repeat it. So therefore, I'm not sure I understood what you're suggesting, but this is basically is taken into account. Problem is actually a well posed. Okay, so what is gaining here is the inverse problem. You see basically you have a finite dimensional data, but you can increase its size to the degree which allows you in two infinite dimensions to identify your infinite dimensional map. So that's basically the whole new idea is this.
Yeah, we'll have to finish here, but any other, well, let's, yeah. Any other questions? I have a quick one, so.
Sure.
You've shown very clearly the, potential limitations, you mentioned the computation time, but I mean, from what I can see, this is actually a very nice method that's completely non-invasive, it's very inexpensive. In terms of the benefits, I mean, am I accurate here? And then whether more benefits that, I'm not.
Yeah, I think this. I had here. I mean, I had a nice contact with Dartmouth Medical School because they made me interested in this problem, and this is yes, still talking with them now in Japan also. So now we would like to add this in Japan. Actually, there is a company which is now talking with them. So yes, idea is just to apply this to medical facilities. But I think one nice wisdom. I think I was one of the colleagues visiting me is an expert in biomathematics. Also know is from Sweden. He gave a nice idea. He said that he also works on this problem, but this wound healing problem, and then this is a kind of nice problem. But then he said that there wasn't a problem. He couldn't, for years find this people to apply this real medical things. And then one of the colleagues gave me some advice. He said that you never go to hospital to ask them to apply your method. You wait until they come ask you, and then you give your method to apply. So that's basically the wisdom of that. So, I mean, there is some truth in that. Yes, there is a connection we have, but I think that definitely this method sounds that it should be extremely useful because it's no chemotherapy is required, also cheap. Doing this method, applying there is no harm at all, and this I think should be the excellent method. But not every medical facility in United States, I know that they're doing this electrical impedance tomography method. Dartmouth is well known, they're doing this. But in Dartmouth, I think, I'm also talking, I hope they will close that they're going to apply this result.
Yeah. Any age, all of a sudden you live, I mean, it seems very robust to medical realities.
Yeah.
Very good. Okay, well, we should wrap up here, but thank you. Thank you.
We're on chat, right? It's union.
Thank you.